We are going live.
Can you guys hear me?
Yes, Amit Vishwas, we can hear you.
We're audible and visible too.
All right, great. So, let me figure out a way to share my screen, I guess.
Your volume is low.
I guess I could try speaking louder. Is that better? Hello?
Yeah.
Hello.
think it
Can
is better.
others hear him clear as well?
Yes.
And can you see my screen? That's the more important thing.
I think we have the required number of students with us, and if we have the permission from Dr. Vishwas, we may start with the formal introduction.
Yes, sir. Yes, sir, your screen is visible.
Okay, great.
All right. So, welcome to the first virtual interaction organized by Aryabhat Foundation. And we have with us for the interaction Dr. Amit Vishwas, who will be interacting with the winners of Aryabhat Astronomy Quiz 2019-2020. Okay, Shreyash Bapat has asked me to wait for another 2 minutes. And then we'll start.
I can't see myself, so I need a confirmation from you that my video is on. And I don't know why I can't see myself. I have not used Meet before, so this is the first time I'm using it.
We can see you, Dr. Vishwas. We can see you as well as your screen. So,
Don't have to call me Dr. Vishwas. You've known me from before that.
Shreyas, let me know when you are ready, and we will start then. All right. So, welcome again to the first virtual talk organized by Aryabhat Foundation. We have with us Dr. Amit Vishwas, and I will be formally introducing him to the students as well as to the online audience we have with us. The topic for today is planet formation, effect of sun's gravity, and significance of studying AGNs or deep sky objects. For the interaction, we have with us the students who were the winners of Aryabhat Astronomy Quiz 2019-2020. And now I will start with the introduction of Dr. Amit Vishwas. So, as you know, as some of you might know, He completed his schooling from Jawaharlal Nehru School, Bhopal, in 2004. Thereafter, he went for his graduation to NIT Surathkal, where he completed his BTech in 2009. For a brief period of 9 months, he was also part of the design and development team of IIA Bangalore and was working for the observatory based in Hanle, Ladakh. After this, he went to Cornell University, where he did his post-graduation and PhD in astronomy. For the past few years, he has been working with the Cornell Center for Astrophysics and Planetary Science, New York, United States of America. So, Dr. Vishwas, the floor is to you. Now you may start your address to the students.
Well, first of all, congratulations to all of you for participating in the quiz and being on the top of the class for this year. It's kind of a downer. I understand that you are not able to visit any of the observatories as originally promised. So this is a stopgap. So I want all of you to make the best use of this opportunity. Ask as many questions as you like. I'm wearing a T-shirt because I wanted this to be informal. My wife told me that I shouldn't be doing that, but I can't see any of your lovely faces, so it's a little bit hard to judge the reaction. So I would very much appreciate if you guys are decent and can turn on your cameras. That would be great. I am, as Divyam said, part of an alumni network, as to say, of Astronomy Quiz, which has been going strong for what now, 15 years?
23rd year was
23rd
completed
year?
last year, and this will be the 24th consecutive year.
All right, yeah. So so I can say majority of my life. Okay. So you guys must have come across a whole bunch of alumni. Some of them are on this call. Alubia is here, Divyam is here. These are the names that I recognize. My memory isn't serving me well if I'm missing out on any of the other folks whose names and videos I can't see on my screen. I can only see 9 people at a time on the screen. So forgive me if I'm not calling you out on here. Anyway, so as I already indicated, I want this to be a very informal conversation. Sure, I'm talking about a couple of different things. One of the topics, which is not my own personal research, I created a couple of slides for, and then I have a video that I can show, and I have a popular science article that I can send a PDF of to you guys. Really, these things that this particular article is written by leaders in the field, so there is literally nothing better that I could find personally in limited knowledge of the details of planet formation. I do proudly represent a department which has historically been on the forefront of planetary exploration, both within our solar system and exoplanets now. So there's some history there, so I feel pressured into talking about this stuff well, because others can probably go online and watch me talk. So anyway, I'll start up a little bit. So basically, the topic that was given to me was formation and evolution of our solar system, and particularly the effect of our sun in how our solar system came to be the way that it is. And so before I go further, and I do want to say that if any one of you would prefer me to talk in Hindi, I can do that. I don't have a problem with that. I might be missing on some technical terms, so maybe it will be English if you guys prefer me to do that. So chime in on that. Happy to hear at any point. If you think I'm going too fast, stop me. If you want me to stay at the slides, I've tried to make them fairly pictorial so we can look at it. You guys can take a look at it too, and then ask questions. Most important thing is this is an opportunity for you to ask questions. Remember that, and don't feel shy. I will not bite. I will not come back with this is a stupid question. There are no stupid questions. So feel free to ask anything that comes into your head, and I'll be happy to clarify within whatever I know about this stuff. All right, so moving on to the very first slide of my presentation. So when we talk about planet formation, this is a process that really goes hand in hand with how stars are formed, right? So this used to be a thing back when I was a kid. We would learn how to write addresses, and then we go from India to Asia, Earth, solar system, Sagittarius, Milky Way, universe. So you know what the scales that we are talking about here. There's a galaxy in which our solar system lives. Sun is one of billions and billions of stars. And then there are these 8 planets and hundreds of thousands of comets, asteroids, minor planets that orbit the sun. Right, that number pretty much changes every day. So there's not much to go into whether there are 8 planets or 9 planets or whatever else the most recent headline might be talking about. So we need to understand what happens when the processes that are involved that lead to basically very tiny gas and dust particles, right, which we are talking about. Dust particles in the interstellar medium are of the order of a micron in size. And these are a typical cloud from which a star forms is of the order of a parsec in size. So just right there, going from a micron dust particle to a cloud in which these particles are sitting, which is on a scale of a parsec, we are already talking about 15, 20 orders of magnitude, right? So there is a whole bunch of physics that can come in and do very complicated things and give rise to, you know, a lot of different kinds of possible options. So we learn science as if it's a wholly deterministic process. Science is based on rules. There are fundamental laws that we can apply. But when you take it to the scales that we are talking about, the tiniest bit of change at any point of time as things are evolving can give rise to a completely different outcome, right? And within the past decade, the thing that we've come to learn is our solar system and planet formation in general is a wholly chaotic process. And that is what the forefront of the field today is. How do we make sense of this chaos? And back in the day, it used to be that our solar system was, you know, the canonical truth of what other planetary systems might look like. Like, we look at our own solar system, we look at the sun, we look at the inner rocky planets, we look at the gas giants that are further out away, and then we look at the cold comets and asteroids that are much, much further out away, right? And it is not wholly inaccurate to think that if our solar system is like this, there might be other solar systems that maybe look like this stuff, right? So now we are sitting in 2020, which is almost the first exoplanet system. I shouldn't say first, I should probably say second, because some astronomers don't like it. The first exoplanetary system that was detected using traditional astronomy techniques was discovered in 1995. And I think a year ago or 2 years ago, the Nobel Prize was awarded for that discovery to people who've been playing a leading role. If you guys want, you can go look up the biography of those scientists who led the discovery of the first exoplanet. Why I said it's not the first is because in 1989, when I was 3 years old, some very creative astronomers figured out that there was something around a stellar remnant, which is referred to as a pulsar. And the pulsar, the one thing that a pulsar has is that it's a very, very accurate clock, and anything that disturbs the pulsar can make that clock tick just a little bit slower or just a little bit faster. And some very, very creative astronomers figured out that a particular pulsar was ticking slightly differently every once in a while, and it was periodic. When it would not tick properly, it would repeat that same behavior in a certain amount of time. And so what they discovered were the very first planets around a pulsar. Whether they'll be habitable or not, or anything like that, we don't know. We don't know anything more than that those things exist, what the mass of those things is, and how far would they be from the pulsar. So those were the very first discoveries. So that's why I hesitated to give you a little bit of history of that. But 1995 was the first time people were looking at a star, and they figured out that there's something that's tugging the star. So every time the planet goes around the star also goes around the planet, which is Newton's third law. And using very sensitive telescopes and instruments, people were actually able to measure that tug, like how massive the planet must be such that it can move the star itself, and we can detect it, right? And what they found was a planet which was much, much more massive than Jupiter in our solar system, but orbiting in an orbit which was much, much smaller than the orbit of Mercury, right? So much more massive planet orbiting very, very close to its host star. And that basically blew people's mind off. Initially, for a few months, they actually thought that it's a glitch. They did not wanted to believe that something like that could be physical, right? And that was the very start of how people came to drive away from the notion of that our solar system is the basis for, or should be used as the basis for, what other planetary systems would look like, right? And since then, of course, a whole phase space of different kinds of planets and around different kinds of stars has opened up, and it really is an industry today. There are thousands of exoplanets that we know of. We're trying to study them in a variety of different ways, and I would probably be slightly foolish if I attempted to talk too much about that stuff in detail. So again, the point that I'm trying to make here is that look at the building blocks of everything pretty much in the universe are identical, and what we end up with is a result of nature playing the chaos game and giving us what we see. So science, the point that I probably want to make most strongly is that science in today's world is an evidence-based study. And the one thing, if you cannot take anything away from all of the stuff that I've been talking about on this very small slide, which has like 8 words and 4 pictures, is that we should always be ready to change our opinions based on evidence, right? And that does not make us bad scientists. That makes us better scientists. If there is a truth that we can uncover and learn from it and add to our understanding, that is the most important thing that anyone can try and do. All right. So hopefully I made my point across for how do we get to Earth or Jupiter or anything in between or beyond. So let's move on to what's the difference between star formation and planet formation. Right? So when you're forming a star, and as I said, right, the basic ingredients are all identical. Right? What you end up with is anybody's guess. Right? So in formation of a star, you have a gas cloud. The gas cloud gets triggered by some mechanism, and there are many mechanisms that can do one thing or the other. And then the gravity, the mass of that of that cloud itself starts to pull material in, and that causes sort of a chain reaction, if you may, right? And so once stuff starts to move, it continues moving, and things get hotter and denser, and that becomes pretty much the core of a star, or what we technically call a protostar, right? And so, as you can imagine, there's this a conservation law, which is called the conservation of angular momentum. When you have these tiny gas and dust particles, which were moving in an orbit of around 1 parsec, and as they start to collapse and fall to smaller and smaller radius, they want to rotate faster and faster as they come closer to, as they come from a larger orbit to a smaller orbit, right? Because angular momentum is conserved. And so what that gives rise to is that this whole cloud starts spinning, right? And then once it's dense enough that it can start formation of a star, what ends up happening is the star provides feedback. The star can emit light. So star provides feedback, and then everything that's not immediately on the star or falling onto it can potentially be driven away from it. Okay, so this phase is called the disk formation phase of around a young star. And then eventually what happens is once the star is able to drive away things which are not in its plane, things condense fairly well onto a disk, okay, and which is in context of our solar system, what we can call is a protosolar disk. And then this disk itself shields the material in the disk from the radiation coming from the sun. Okay, so stuff in the disk is protected by all the other stuff in front of it from the disk. So this cannot continue all the way in, as you might be wondering. So what happens is that the sun clears out a hole in its immediate vicinity, right? Everything sort of like if you light a match, right? And you put paper closer and closer to the match, at some point the paper will start burning, right? So the sun clears out a hole, everything beyond that gets heated up, and as you move further and further away from the disk gets cooler. So other physical processes can take charge, right? And so I tried to put in a little bit of things in words, in difference between star formation and planet formation. Similar forces are acting, similar processes are happening, but there's one very important difference is that the sun can once a star is formed, it can actually provide feedback, whereas planets cannot exert any other influence, any influence other than their gravity itself, right? And in order to exert that influence, they have to grow, and growing planets is a really messy process. And to be very honest with all of you, we don't exactly understand what causes planets to get to where they are. Okay, this is an active area of research. We are still trying to figure. There's something called the centimeter scale crisis or the pebble scale crisis. If you want to look up online, feel free to do that. What we don't know, so we have a lot of very nice numerical recipes that we can put into simulations, which will cause the size of particles to go from centimeters to meter scale or boulder scale. But in physical reality, how do those numerical recipes translate to something real in the world is not understood. There's very little observational evidence. If it works one way or the other, typically it's a combination of many things. And so our observational understanding is rather limited. So mostly we are driven by our more primary understanding of how laws of physics work and putting that into a computer simulation and trying to understand what's the output of it. And as I said, if anything changes on a particular instance in time in your simulation, the result that you see can be completely different, right? Because it's mostly driven by chaos. All right, so moving on to this, so there's a really long road from dust to planets, and what we can actually observe are these things which are from a micron size to a millimeter size. And these observables we can see not only on our solar system, but also in exoplanetary systems. We have enough sensitivity, different kinds of instruments that can give us knowledge of the aggregate, an average of what is the stuff that's sitting there. So what we don't understand is how do bodies go from right around here, centimeter scale, to 1 meter scale. And then things can, gravity can take in charge and really quickly build up these particles from meter to kilometers or hundreds of kilometers. So that leads us to comets and meteorites and asteroids, kind of things. And then further in, gravity really wins over at that point. And once you have a massive enough core, it can accrete material around it to bring you to a rocky planet or a gaseous planet. Now, to form gas giants is a tricky process. Planet formation, if I have not stressed enough, it's a very delicate process. So most of the young stars that we have observed, okay, they are typically in a range of about just under 1 million years old to about 10 million years old. Okay, and astronomically, this is a very, very small amount of time. Okay, stars lives for billions of years, most of them anyway. Okay, and so what we find is that this disk that I was talking about, this disk really has a lifetime of about 5 to 10 million years, right? So most of the planet formation action has to be done by the time the disk is dispersed, because once the disk is gone, all the material with which you were going to form the planets is gone. Okay, only the stuff that the big brothers, so to say, or sisters in the planet that kept together in the disk, right? These cores for proto-Earths or cores for gas giants. These are the things that can keep material right around them, sort of their own nebula, so to say, and then give rise to what happens in the future. Okay, so you need to understand that all the gas giants need to finish forming by the time this disk is gone, because by the time the disk is gone, the gas is gone, and gas giants are all gas. Okay, rocky planets have a little bit more time to have further interactions from things that are being thrown out by more massive bodies, and so on and so forth. But gas giants are very delicate. They're very, very fickle. All right. So this is what I've tried to put together on this slide here. So you start with dust, stuff brings things together. We get up to protoplanets. Protoplanets are already in place by the time the disk is about 1 million years old, which is the limit of when we can actually observe these disks. We cannot observe them any younger, because before that, the protostar is completely dominating everything. So you can't really see the details of what's going on before that. And at that point, if you have enough gas available in the disk, you can have runaway gas accretion and form these gas giants, or you can have some more gentle processes going on in the disk that will give rise to and create rocky planets like what we see in our solar system as Earth, Venus, Mars, and Mercury. All right. Okay. So with that, I think that's pretty much all I have for planets. I said a lot of things, so I'm expecting a whole lot of questions.
Right. Anybody who has questions can write it in the chat box that I have a question. Then I will ask you to open your mic and then ask the question. We can also take questions from the online feed, which is going on the YouTube, and we have a sizable audience right now there.
Right.
Yes, Roshan. Okay. Some issue with the Roshan. Roshan might join a bit later, and then
you can unmute yourself and ask the question as well. I don't mind that. The powers to be don't mind that.
I guess Lucky also has a question.
Can I ask the question now?
Yeah, go ahead.
So, sir, when the gaseous planets form, the case that you told about the hot Jupiters, their orbit is smaller than the Mercury's orbit. So, when they migrate inwards, they stop at a point. And if they go on, they will go into the star. But they stop at a point. What causes
Not
that
always.
halt?
Not always.
Yeah, not always, but
Yeah. So that's actually one of the largest focus of theoretical studies in the past 5 or 6 years has been the migration of hot Jupiters, right? And the idea is in a whole lot of solar systems, most of the gas planets actually form much, much further away from the star. Okay, and then because there is, in case there is nothing else for this massive planet to interact with, it will be stable. It will just keep sitting there, right? There is no reason why this planet should start migrating inwards unless there is another, I should be careful in the term that I use here, unless there is another perturbing force that causes it to move from its very stable orbit. Okay, so in gravitation, you can solve a two-body system perfectly. Okay, the orbits are stable, everything is nice, you don't have to worry about anything. Once you have a solution, it's a stable solution. But as I told you, nature loves chaos in the sense that when you're actually forming things, it's not happening in a vacuum. You have the star, which itself is evolving also. Okay, so there's stuff migrating onto the star, even when the gas giant planet is forming. And there might be other planets forming in the disk. Okay, and depending on where they are, so I would classify them as in their orbit. Let's say this gas giant is orbiting at a 10-year orbit, and there's another gas giant that's forming at a 6-year orbit. Okay, so every few years, these two planets will be able to interact with each other when it just happens to be when they line up. Okay, when they get on the same side or exactly the opposite side. Okay, so there's a different kind of tug that other planets that are also forming in the solar system or in the planetary system that exerts on these gas planets, right? So as soon as you introduce a third body into gravitation, it becomes a problem that you cannot solve symbolically. So like you can't just type in a bunch of equations and get an answer which is exact. You always have to solve them numerically. Okay, and what you do is basically you set up some initial conditions, and that's why studying these things has been the focus of theory. And people have come up with very, very interesting results in the past few years. Actually, one of the results is a better understanding of what gives our solar system the architecture that it has. Okay, like when you look at it, why are Jupiter and Saturn in the places where they are? Why are most of the objects that are further away from the gas giants in highly elliptical or highly eccentric orbits? Right? Pluto's orbital plane is shifted from the orbital plane of most of the other planets. All of these things, each of them give us a hint to how the solar system evolved. Okay, so in a lot of cases, what happens is that the hot Jupiters that we are seeing very close into the star, they have been triggered in that place by another body in that system. Okay, now sometimes that body is massive enough that up to a point that planet can keep falling in, and then this body just happens to have another interaction with this thing, and they both will pull each other out of this death spiral, or it can give it another push and make it fall in. There have been observations of some planets which are too close to survive, in the sense that there are predictions that these planets are actually actively evaporating away. Like the gas temperatures on the surface of these planets are so high that there's just no way that they'll be able to survive in the orbit until beyond a few hundred years. And so if there are observers still left on planet Earth a few hundred years down the line, those things can actually be even verified. Those predictions are actually fairly accurate. And given the time scales, chaos cannot win over, that something can come in and magically save it. Like once you get into this death trap of gravity, it's very difficult to escape. So you can identify where is the death trap a gone case and where you still have some hope. And so that's where chaos theory is a whole lot of planetary dynamics these days. If you want, if you just type in chaos planetary migration, you'll see 1,000 papers.
Okay, we have a question from the live YouTube feed from Savita Saikia. She's asking, what is the self-gravity? Also, we have Shashwat Pandey. He's one of the winners. He wants to ask a question. Shashwat, you can unmute yourself and ask the question.
So let me quickly finish off the self-gravity part, which is I guess it's an easy enough answer. The self-gravity is own gravity, right? The mass of the thing itself that allows it to attract things within its own radius of influence. So for a micron size particle, that radius is really, really tiny, right? Because it weighs a few micrograms at most, right? But as you keep increasing the size of this particle, right, a bunch of different dust grains can attract each other electrostatically, for example. Right? There can be residual electric charge, and electrostatics is a much stronger force than gravity. Okay, so these things can stick together and start forming a bigger and bigger conglomerate, and then gravity can start helping. So self-gravity is pretty much that. It's whatever you can do by your own mass. All right, next question.
Right, Shashwat, you can unmute yourself and ask the question. Shashwat, you can unmute yourself and ask the question. Shashwat Pandit. All right, if you're not able to unmute yourself, you can also write it in the chat box. We also have a question from the live feed from Sajal Kapoor, which is, sir, what is runaway gas accretion?
Sorry,
Sorry,
not clear.
got it. I just realized that. All right, okay. So runaway gas accretion is one of the two leading theories of giant planet formation, and basically what it tells is that if you have a gas blob massive enough, okay, which is, I think in simulations people have figured out that roughly about 1/100th to even 1/1000th of the mass of the star itself. What you can do is you can create a local instability in the disk, right? So this disk has a bunch of gas sitting in there, right? And the biggest body that's at play is the star itself. So this gas is moving around the star itself, right? Now, if you make a planetesimal or a planetary core heavy enough, I think the number typically given is a few Earth masses. What you can do is you can create a local instability that can start pulling in gas that's otherwise only going around the star onto itself. Okay, and once this funneling starts, remember gravity is directly related to the mass of the object. So this funneling basically becomes a runaway feedback, right? So whatever caused this funneling of material onto this planetesimal was the mass of this planetesimal, okay? And once gas falls on it, now the mass of this planetesimal becomes even larger, So it becomes even easier for stuff to funnel onto it. And so that's what is the runaway gas accretion. Accretion means falling onto, and the runaway is that there's basically nothing else stopping it unless there's some other physical process that happens in the disk that cuts the supply of gas accretion onto the planet, or the star itself does something violent which cuts away the supply of the planet. And again, really, the details of these are all over the place. But so far, for giant planet formation, there are really two sort of stable enough solution loci that you can find. One is a core accretion, in which you form a solid core first, and then stuff falls on it. And the runaway gas accretion is just a blob of gas, which was able to, by chance, become heavy enough that it start funneling more gas onto it. So that's actually one of the main questions that there's a mission around Jupiter right now called Juno. That's one of the main questions that Juno is going to answer, is figure out whether Jupiter's core is massive enough to conform with core accretion or the gravitational instability. We don't know what Jupiter's core is made of exactly. We know what its density is and how big it is. So we know what's the mass of it, but we don't know whether it's metallized helium and hydrogen or whether it's rock. Because the kind of pressures that it's under, we can't even replicate those pressures on Earth to understand what happens to hydrogen at those pressures. All right, I think there are a bunch of questions now.
Yeah, we have a question from Manas Sahu. Manas, you can unmute yourself and ask the question.
Yes, Bhaiya, is it possible for rocky planets or gas giants to be on the rocky sides?
There is no reason why all the planetary systems should look like our solar system. And I think that's one of the first things that I was trying to emphasize on, is that our solar system is, you took 100 coins and you tossed them, and our solar system is just one of the patterns of heads and tails that you can potentially.
Yes.
And there are cases in which there are certain exoplanetary systems in which we have found more massive planets on the inside or closer to the star, and slightly less massive planets on the outer side of the star. I would say that this the chaos argument that I was trying to make, if the more massive planet is closer to the star, that means that its orbit is shorter than
yes.
all the other planets that are in the same star's orbit.
Yes.
So this more massive planet will have a much higher frequency of interacting with everything that's at different orbits, and hence throwing chaos, or hence allowing chaos to be a more dominant player at that time. And I will show you a simulation video. Or what I can do, I think better, is just send you guys the link to that video so that you can take a look at it at your own convenience, because there are a lot of details in it, and it's a really beautifully made video. So I'll post a link to that video in here that deals with, in particular, the evolution of our solar system.
Okay.
I typed that link in the chat here. You got that. Okay, so I think I see a couple other questions here. There's one from Pragati Thakre, which says, why only the inner planets are made up of rocks and only the outer planets are made of are gas giants? In case of our solar system in particular, the currently accepted theory is there's this thing called the giant tack, that Jupiter and Saturn, they decided to take a hike through the solar system, and they came very, very close to the inner edge of our solar system, which is basically around the orbit of Mars. Okay, and then very fortunately, Saturn just happened to interact with Jupiter at the right point in time, such that they locked each other in a resonance and then they drifted outwards. Again, I'm trying to emphasize it was only a matter of chance that Jupiter and Saturn were in the position where they were, and they then migrated outwards, leaving only the rocky stuff closer in. If that wouldn't have happened, there are potential scenarios that people have actually simulated that if Saturn was not at the right place at the right time, 800 million years after the sun's formation, things could have ended up very differently. And why we think that that is the right answer is because you can count craters on the surface of Moon, and depending on how smooth the craters are, you can figure out how old they are. And even if you can't do it very exactly, what you can do is you can figure out at least a number distribution of how many craters, how smooth, and you can see that there is an uptick in very smooth craters, and there's a huge number of them, which happens to exactly match this 800 million year time frame when Jupiter and Saturn were dragging each other out. And while they were doing that, they were basically throwing everything in the solar system that was going around the sun in a crazy orbit. So this period is called the period of late heavy bombardment. And it's very likely that Earth life was seeded on Earth during that time. Most of the water on Earth was delivered during that time too. Earth did not have water in situ. If you did not know that, fun fact.
Okay, we
All right, I have a couple other questions here. Actual reason that accretion caused a planetary system? Well, the actual reason is always gravity. Anything to do with astro, gravity has a role to play to start and to end. There are magnetic fields that come into play every now and then, and that's most people invoke any other argument other than gravity only when things are not making sense. And earlier, back in days, like when I was much younger, people didn't like to invoke any other things because you could not simulate those things in computers very efficiently. Now, because we have basically a supercomputer in our hand, what would have been a supercomputer in the 90s in our hands, people love to add more complication into models. And that has led us to a much better understanding of how things go on.
We have
All
a
right.
question.
What's the next question that I have? Sorry, Divyam, go on.
We have a question from Sameep Modi. Sameep, you can unmute yourself and ask the question.
Yes.
Okay.
Sir, is there any possibility that a gas giant becomes a star?
Well, that's a very interesting question. So there is this fuzzy boundary of at what point can you start hydrogen fusion in the core of an object, right? And once you can do that, what you call that object, which is now self-luminous, a star, right? There is a second fuzzy-ish boundary of when you can start doing fusion of, trying to remember what was it, tritium, I think. I'll have to check on that. Sorry, I'm blanking out here. But basically, anything that's about 11 Jupiter masses can fuse a different variety of hydrogen, a different isotope of hydrogen, and can be self-luminous for just a little bit. Those things are called brown dwarfs nowadays. And so they can be self-luminous for a little bit amount of time because you have this source of energy, but really the source of energy runs out very quickly because the other isotope is much less abundant than hydrogen, which is harder to fuse, by the way. Sorry, you were saying something?
No, sir.
Okay, right. So Jupiter cannot do any fusion. Okay, so why a star starts undergoing fusion is like if you were to imagine that gravity is the only thing that's at play, materials falling, things are becoming more massive, right? And as you can imagine, if I were to put a brick on your head, you will feel pressured by it, right? If I were to put 10 bricks on your head, you'll feel more pressure, right? Similar pressure is felt by atoms. If you were to put enough mass on top of a layer of hydrogen, it will feel enough pressure or enough gravitational push that it can fuse. So really what's happening is gravity can help a quantum mechanical process of two nuclei interacting with each other and just enough to form a helium nucleus. And to create that kind of pressure, to create that kind of temperature, you need a minimum mass. And that minimum mass is canonically called Jeans mass, based on 19th century astronomer. Jeans really like the pant jeans. So you can figure out at what time is a body self-supported by gravity. And then you can take that argument a little bit further and what time the body can start undergoing fusion. So Jupiter cannot do fusion. The minimum mass that you need for hydrogen fusion is about half a solar masses. Again, this is where I'm rusty. The last time I took a planet formation course was a few years ago. At least 5. I can look that up very quickly though if you want. Anyway, next question. I'll come back to it if I figure out.
Next, we have a question from Shashwat Pandey. The question is, why is Pluto much farther away from rocky planets and not in sequence?
Well, as I was trying to say, right, that's one of the reasons why Pluto is not considered a planet anymore, is because there's a whole population of minor bodies on the outskirts of our solar system, which share their properties with Pluto, to be very honest. And we really only started discovering these bodies in the late 90s. And so that's what we call the Kuiper belt today, right? And the Kuiper belt is like the inner extension of the Oort cloud, which is whatever was left over after the planet formation craziness was able to go through. So Pluto is a part of the Kuiper belt. It is a Kuiper belt object, KBO, if you are looking for something. All right, I did find the answer to minimum hydrogen burning mass. That's about 1/10 a solar mass, so 0.08 to be exact. And can someone do the conversion of how many Jupiter masses would that be? What's the mass of Jupiter in terms of solar masses? It's like 300 or something. Is that right? Pop quiz. Sorry. I didn't want to put you on spot. Hey, that's okay. You can figure it out yourself later. All right, next question.
Okay, we have a question from Utkarsh Singh. Utkarsh, you can unmute yourself and ask the question. And then thereafter, we will take some questions from the online round.
Okay.
Utkarsh.
So why do planets spin in the same direction in our solar system on its own axis in which the sun spins, excluding Venus, which rotates from east to west direction?
Well, so Venus's spin is more an anomaly than the rule. As I mean, that was your question. Sorry, I just repeated it. But there are the other examples of planets not rotating in the same direction as the rotation of the sun, for example. Neptune is one good example, and the reason that we think is most likely behind it is that sometimes my parents tell me that I was dropped on the head when I was a kid. So That's pretty much the same reason that we use for these weird planets, weirdly rotating planets. Now, the question about why almost everything seems to be in line with the rotation of the sun, I'll go back to the argument I was trying to make earlier about the conservation of angular momentum, right? So you have to think about, you don't form a star from a disk. Okay? You form a star from a fuzzy cloud. It has no special shape. Okay. What you do is, once you have enough of a seed mass, it starts pulling material onto itself. Okay. And where is this material coming from? From slightly further away from where the seed was. Okay. It might not have any preferential direction. It can either come from the right or from the left, top, bottom, anywhere. Okay. But once this material starts to fall onto the seed, this seed is basically giving it a preferential direction to move in, right? So before, everything was flying in every what direction. It didn't have any preferential direction, so to say, right? Whereas now that you've given this seed, made the seed heavy enough to pull in gas, a lot of the gas in its radius of influence now wants to move in this particular preferential direction, okay, and fall onto this massive enough object. Now, as it moves from larger radiuses to smaller radiuses, I talked about this conservation of angular momentum, right? So this seed might not be spinning by itself at first, but now that it has accumulated this one extra atom or few extra atoms of gas from further out, now it has a little bit of angular momentum. And how does the star conserve the angular momentum? Is it starts to spin on its own axis. Okay, all right. Now, this spinning on its own axis gives other material that's streaming onto the star. Like if stuff was falling in from the top, it could make it onto the planet easier. Whereas if material was falling in from the side, it would sort of streamline around the star. Okay, very much like if you played car racing games, there is this thing called drag. Right, the flow of air is easier in the wake of the thing that's moving. Okay, you reduce your air drag if you're driving right behind another fast car, for example. So it becomes easier for material to make it in onto the star from the sidelines. Okay, so it's imparting it this tangential velocity, which spins up the star even further. So every time, it's like imagine like you're holding a disc with a stick in the center, and you're spinning the disc one at a time and tangent to one of the radiuses, right? And what you end up doing is you really start to spin the disk very fast. And so physics allows for one process to be slightly more efficient than the other process, and this builds up over 1 million years, makes the star massive enough. And so now understand, like even when the star has formed, right, gravity of the star is still the dominant force, even though the radiative feedback of the light that it's emitting might be creating a hole in its immediate vicinity. This star is the thing that's keeping everything else around. Okay, so basically that is the reason why this fuzzy cloud collapses. Once you have a star or protostar forming, it collapses into a disk, and then the radiation from the star evaporates that disk very fast. So this preferential rotation or directionality is imparted at the moment of, or I should say, during the phase of creation of the star itself. And that's why you see these things to be so well organized, so to say. So unless something chaotic happens, things remain aligned. For example, Earth is not exactly aligned with the sun's axis of rotation. Earth is about 20 degrees off, right? And you can very easily explain it if moon was formed due to an impact. It's slightly harder to explain it other ways, but perfectly reasonable to do it that way as well. Actually, that's why there's still debate about how the moon was formed. There's no one theory that explains how moon was formed.
Right. It's time to start with the online questions. We have a question from S. Mansi. Question is, huge bodies are pulled together by gravitational, but how do small dust particles come together?
Small dust particles, during the very nascency of their interaction, are almost always pulled together due to electrostatic charge. There is, it's fairly easy, and if you're aware with the effect for which Einstein actually got the Nobel Prize, photoelectric effect, it's fairly easy to extract an electron from a hydrocarbon and create a charged hydrocarbon. Okay, or for that matter, if you think of basically these dust particles mostly are microscopic lumps of coal in most cases, right? The ices that we know of that form most of the interstellar medium, they're either carbon-based ices or water-based ices, right? And in both of these molecules, it's fairly easy to pick out an electron from a conglomerate of it. And so electrostatic forces can pull these things together. And really, those are the only forces that are strong enough to allow you to act fast enough, because these electrons that you have pushed out from the surface of a dust grain, these electrons can fall back and recombine and make it neutral, right? Because if you have taken charge away, now you have the attractive electrostatic force. So there is a time scale over which the electron will come back and recombine, and there's a time scale over which these two dust grains can migrate towards each other and combine. And really, it's a fight between electrostatics and electrostatics, and more times than not, it's basically a rate of reaction, like what is preferred. And more times than not, thankfully for us, the stiction of grains wins out. I think I had, yeah, that's what is referred to as aggregation and coagulation here for the micro to centimeter sized particles. All right.
Right. So we can move to the next question. These are the last two questions for this first topic, and then we'll move to the second topic. The second last question is, what is galaxy distribution function and how is it used? This question is from Astrophile 247.
Well, a distribution function in general is you measure a property of an object. For example, if we are talking about dust grains, you can measure the size of dust grains, okay? And then you can count how many such dust grains are, and you can start putting them in a bin. You create a bin in which you are going to count all the dust grains which are 1/10 of a micron to 1 micron. You can create another bin in which you count all the dust grains that are 1 to 5 microns. You can create another bin in which you have 5 to 10 microns, so on and so forth. And you start putting in every dust grain that you put it in a different bin. And once you have created enough, large enough a sample that tells you something about the object that you're trying to study. For in this particular example, it tells you something about dust grains. Similarly, for galaxies, you can have a distribution function that's based on gas mass, dust mass, stellar mass, dark matter mass, black hole mass. Think of any property that you can associate a galaxy, right? And similarly, you can do this you can apply this is a statistical concept, right? The idea is that once you have looked at enough range of the property that you are trying to understand and you've cataloged it, that tells you something about how those things came to be. Okay. So for example, if you're looking at galaxies, typically what you find is that you find the number density of galaxies which are up to a certain mass, more or less fairly uniform. But beyond that mass, if you're looking for really, really massive galaxies, the number densities of such galaxies falls off very fast. So they are much rarer objects than smaller or less massive galaxies. So in terms of stellar mass, this knee occurs right at around 10 to the 10, 10 to the 11 solar masses, which happens to be the solar mass, the stellar mass in our own Milky Way. So our Milky Way is a very normal, average kind of galaxy. Okay, so distribution functions, the concept is that you take a property, you measure enough of it, and then you try to understand from physics and whatever your understanding is of things, like what put that distribution in place. Astronomy is very a very evidence-based science or observationally driven science, that we don't necessarily know what we are looking at, but once we have looked at enough kind of those things, we can start and build together a picture of it. Okay. Is that a good enough answer?
This question was from the YouTube chat, so maybe we'll get a reaction from this a bit later.
All right.
The last question we are taking for this topic is from Yashovardhan Gwale.
Mhm.
The question is, sir, you said that gravity helps in triggering the nuclear reaction in gas giants. Can you
Yes.
elaborate more
Not
about
gas giants, stars. Gas giants don't have any fusion going on inside of them. So sorry if I conveyed that meaning. Gravity is the reason why stars have fusion. It's everything that fusion requires is a consequence of the stars being the mass that they are. If they were not massive, they would not have fusion. They would not have the high temperatures in their core that allows them to have fusion reactions. So clarification.
Okay, so now we can move on to the next topic for today's session. I have a lot of questions coming in on the YouTube as well as through the students. But then we have a time constraint. Move on to the second.
So I actually wanted to flip the tables a little bit on for this topic, because this is a topic that I personally do research in. So I feel much at ease just being able to answer questions. What I would do though is I can plant a seed for questions. Okay, and that seed is very, let's say, things that while you participated in the quiz, you would have come across. Okay. So this is probably a little bit isolating to the YouTube live audience, but I guess this is really the moment for the winners of the quiz here to shine. And so what I want to go back and ask you guys is, what's your favorite deep sky object? Okay, and so how many quiz winners do we have here? And I think there are like 15 people, right?
Right, top 15 are here.
Right, so let's do starting right at the top. Whoever tell me what your favorite deep space object is. I'll tell you something about it. And
M45.
M45, please. All right. Do you know what kind of what kind of deep space object it is? Do you know anything more about it?
It is a Messier object found by Charles
Mhm.
Messier.
Okay. All right. So that's very much like the discovery aspect of it. But what it is actually open cluster of stars. So what you see as M45, the Pleiades in the constellation of Taurus in the sky, is actually a star forming region which would have existed about 70-ish million years ago. It would have looked like a nebula. Most of the stars in the Pleiades cluster are fairly young. Did I say 70? It should be more like 200-ish, I think. But anyway, so we have studied the stars in the Pleiades cluster in detail enough that we know the stellar ages of most of them, actually. We know that it's not very young, and when I say very young, it's not 5, 10, 15 million years ago, because we don't see any very massive stars in there. And the only reason why you would not see very massive stars in Pleiades is either they didn't form at all, or they did form, but then they went supernova, right? And massive stars go supernova very quickly, right? So within the first 10 to 15 years, all the stars above 10 solar masses or 12 solar masses are gone, poof, okay? So when you look at an open cluster with such amount of nebulosity that you're actually able to see through in your telescope, you're looking at a physical aggregation of young stars, and the nebulosity that you see is actually ionized gas that has not been completely dispersed away from Pleiades. Fun fact about Pleiades is the distance to the Pleiades was up for debate till about a year and a half ago. I'll leave that as something for you to go in and check. There's a mission called Gaia that really nailed the answer to that question. You'd be surprised the technique with which they nailed that answer. It's a really simple technique. All right, who's next?
Yeah, what about Horsehead Nebula?
Horsehead Nebula. Horsehead Nebula is part of a much larger star-forming complex in the Milky Way. Okay. And actually, I tried taking a picture of that complex a few weeks ago. Was not very successful, but let me see if I can pull up a picture of it. But anyway, the Horsehead Nebula is actually it's a reflection nebula. So basically, most of the stuff that's exciting in the Horsehead Nebula is actually covered by a really thick cloud of dust. So we really can't see through it. But you can see associated star formation activity in Orion Nebula, which is M42. You can also see most of the stars in Orion, though, are not really associated with the Orion molecular complex. I'm trying to see if I can find a good picture of it. It really is an amazing place to start studying deep space objects. Well, they're not necessarily deep space because they're all within the Milky Way, and I think typically people make the distinction of deep spaces when it's outside the galaxy. But I will tell you this, that if you were to go in and study anything astronomy, you are bound to run into studies of the Orion molecular complex, Orion Nebula, because it hosts everything that astronomers want to study. Every kind of phenomena, young stars, protostars, dust, nebula, ionized gas, whatever you can think of that astronomers want to study in detail is available in the Orion Nebula. It's close enough. There are enough kinds of sightlines that you can try and study things from different angles. And so the first couple of years of my PhD were basically hearing from my advisor how he studied Orion Nebula in the 80s. And now everything that we do is basically, yeah, what was that number in the Orion Nebula? Multiply it by this much, that's that in the galaxies. And this galaxy is like 50,000 Orion Nebulas, right? And you'd be surprised how many papers are written in extragalactic astronomy today, which cite exactly this sentence that I told you. And it's not in vain. I said it sort of laughingly, but that's no joke, really, because Orion Nebula is kind of our extragalactic dictionary. Like, you can study and pinpoint really fine details of processes in different parts of the Orion molecular complex, and you can apply what you understand from them onto things that you cannot see the processes in as much detail. Like galaxies are galaxies because they are much farther away than what the distance to the Orion Nebula is, or Orion molecular complex is. So, but because it provides us, it's sort of what could be called a Rosetta Stone for astrophysical processes. There are literally books written about stuff, which is actually one of those books is called Astrophysical Processes. And that book, in every chapter, cites, okay, here's the physics, here's what we saw in the Orion Nebula. Go figure, right? And so it really is, it's an amazing place to start anything astronomy. And because it's up in the winter, we get to see it a lot. All right, next.
Betelgeuse.
Sorry, sir, again?
Betelgeuse.
Betelgeuse, okay, yeah. Well, it has been in a lot of news in the past year. Anyone knows why?
It's gonna blow up into a supernova.
Aha, that's what people want to say. So that's one of my pet peeves with headlines related to astronomy, is that they always say astronomers were puzzled by this, astronomers were blown off by this. All the extreme adverbs and adjectives are used to describe anything astronomy. It's not that. I mean, it's really at the basis of it, it's all physics. Right? We understand how things work. Right? It's just that we saw a galaxy that's so bright. That's great. It's a rare object, so we put it in the news when we see a rare object. Of course, we'll do, right? If you were to go in and take a picture of the last tiger alive in India or something like that, God forbid that happens, that would be in the news too, right? It's a rare object. So that's why you see so many extreme headlines related to astronomy. But that question is actually solved. Fun thing is there are lots of different pronunciations of this thing in my head, so that's why I stumbled there, tongue twisted a little bit. Betelgeuse, I don't know, whatever you prefer, but right. It is a red supergiant, okay? And it is indeed towards the end of its normal life cycle, right? What's actively happening on Betelgeuse is it's shedding the outer layers of its what's called the stellar atmosphere. Okay, so people have actually taken pictures of Betelgeuse at very different wavelengths, and they see that Betelgeuse has been having these burp events. You can literally see an onion layer-like structure of things that are moving away from the center of the star. Okay, and what happened in the past few months is that Betelgeuse dimmed down by almost half a magnitude, or three quarters of a magnitude, which is a large change in brightness for a star, right? So of course, people jump to the more exciting conclusion that it's going to blow up, something weird's going on the star. Unfortunately, back in February, this was already addressed. What ended up happening was people took a spectra of the star as soon as they had time available on a big enough telescope that can give you the details. And what they figured out is between November or October last year and December this year, or I should say February this year, when they took that spectra, something came between the line of sight from us to Betelgeuse. Okay, and that something was a cloud of dust that Betelgeuse burped out. And that's a very normal thing to happen in the life of red supergiants. It will very likely go supernova in a few thousand years, maybe 10,000 years, but maybe tomorrow. So it's going to be an interesting star. It could be a very interesting star in our lifetime. All right, what's next?
Sir, the Eagle Nebula, the pillars of creation it has.
Right. So the particular reason why Eagle Nebula is so popular is because Hubble has been taking a picture of it for almost every major anniversary that Hubble had. Oh, I see someone sharing a picture. Yeah. So this is the headline that came out yesterday.
Yeah, I think this was very recent, day before yesterday.
Yeah. But the second sentence in the abstract of this paper is, there was a paper by Lewis and Massey in February 2020. They figured out what we are going to say in this paper. The only new thing that they had in this paper was they added a couple of new HST images, which is good and fine. But yeah. It's again, right, evidence-based science. There was a little bit of what do you call a speculation part in the paper that came out in February, because in spectra you can't really see the dust shine out that quickly, because all dust is doing is putting away in between you and the star. And so these pictures really, again, and these pictures in particular that you're seeing are artist representation, just to be clear. But in the HST images, you can sort of see that the thing that's doing the veil is physically disconnected from the star itself. All right, what's next? I can send you a paper of the Lewis Massey paper.
What about the M22 globular cluster and Sagittarius?
Wait, hold on. I hear your question. I want to go back to the pillars of creation again. The very interesting part of the pillars of creation is, like, if you really zoom into those pictures, you see sort of where the fingers of God are. There are these tiny things that are separating off from the fingers of God. And those tiny things are called proplyds, or protoplanetary or protostellar disks. It's basically the very earliest phase of the formation of a star. And they appear dark in Hubble visual images because most of the stuff hasn't fallen into the protostar. Right? So it's gas and dust that's covering the actual protostars that are inside. Right? So once the star starts shining bright, it will either have that material fall all the way into it, and or blow away the rest of the material and expose itself out from this cocoon. And so M16 is a very good example of the earliest phases of star formation in action. Your question was M22 globular cluster? Whose question was it?
Yes, globular cluster M22.
Don't know it by name, but let me look it up. M22. I do remember M13. Right. What I can tell you is globular clusters are another very interesting type of objects, and they actually tell us a whole lot about the mass that we cannot see in and around galaxies. And fairly easy to study them around our own galaxy because there are so many of them and they're typically away from the galactic plane, so we can study a good number of them. But we can also study globular clusters around, for example, the Andromeda galaxy. If you didn't know that, now you know it. It's really interesting because globular clusters are old enough that they are believed to be the earliest remnants of how the galaxy came to be. Right? And the reason why they are in these places away from the galactic center, I come back to the planetary talk that I just gave. Similar processes apply to galaxies too. Right? It's just the scale of the cloud from which a star formed was about a parsec. Scale of the cloud from which a galaxy formed is megaparsecs. This density of the cloud from which a star forms is few hundreds, maybe few thousands particles per centimeter cube. The density of the cloud from which the galaxy forms is maybe probably 1/100th particles per centimeter cube. Right? So there's a whole lot of mass because the volume that you're occupying is a megaparsec. Okay? And imagine like all of these arguments that the dynamical timescales for planets are tens of millions of years for formation of the systems. So imagine when you scale up from a parsec to megaparsec, but you also scale up the mass from 1 solar mass or half a solar mass to 10 to the 12 solar masses, you change the dynamical timescale at which things are happening in the galaxy. So galaxies are actively evolving, and actually most of the galaxy clusters that we know of today in the universe, they are not even in what's called thermal equilibrium. So gas in those galaxy clusters is still funneling in and out and through the galaxies, and the formation processes are still going on. Okay, so how that ties into globular clusters is globular clusters, given the location that they're in, and they are staying there, they're not moving from there, right? We've actually been able to track the orbits of globular clusters around the center of the galaxy. So we know what's the path that they're going to take over tens of millions of years, okay? Or hundreds of millions of years for that matter, depending on how far away they are. So they really track what was the earliest extent of the cloud from which the galaxy was forming. And because stars can form at a much quicker time scale over which the galaxy is settling down, all the stars that you're seeing in the globular clusters were probably formed in situ when the galaxy did not have a disk that we believe the Milky Way has today. So all of these globular clusters are sitting out in the halo of the galaxy, and they are what is actually tracing most of the dark matter. And that's actually another way, the motions of these globular clusters is another way that we can figure out what's the dark matter mass in the galaxy. All right, what's next?
The voids between the galaxies. Is there interesting something there?
That ties in very nicely from the galaxy formation perspective, is that while you have these clouds which are a megaparsec scale, right? You also have these voids which are of the order of megaparsecs between galaxy clusters. And think of number. There is a canonical number which actually comes from, which is seeded from the Big Bang. That number is, I think, of the order of 100 some megaparsecs. Okay, and galaxy clusters are separated by roughly this distance in any direction that you look in the universe. Okay, and the reason for that is this is basically a blown up canvas projection of the matter inhomogeneities that were imprinted at the end of the inflationary era of the universe. So within the very first second, and actually when I say the very first second, 10 to the minus 40 seconds from the moment when the Big Bang is supposed to have taken place, inflation basically imprinted a structure on the tiny bubble that our universe was at that time. And then at the end of inflation, which is 10 to the minus 30 some seconds after the Big Bang took place, this bubble was many, I think I'm forgetting the number, but many parsecs large, at least. Probably much larger. I'm blanking out on this. This makes me look stupid. I should know this. But anyway, so it's during the era of inflation, which was a very tiny amount of time, very early on in the history of universe. There were some places where you had just the tiniest little bit extra matter or radiation sitting, and there were places in the immediate neighborhood of it which had the tiniest little bit lesser amount of matter. And so if you look up the map of the CMB, what you can see is that that same structure basically stretched out at the time when the universe was about 380,000 years old. Okay, what's the scale of the universe at that time? I don't exactly remember, but you can look at the rate of expansion of the universe, and you can figure out if things were separated by this distance at 380,000 years after the Big Bang, what would they be after 13 billion years, right? And it matches perfectly. And so voids are basically just a consequence of whatever happened in the era of inflation. This tiniest extra bit of matter that got stuck or was not there gives rise to all of the large-scale structure that we see in the universe today. All right, next question.
Utkarsh has a question. I guess we're about time we wrap this up. Last few questions. Students who haven't spoken yet can come up with questions and yes, interact. Utkarsh.
Yes, the sun is made up of hot gases, and in the polar region of the sun, it takes 30 to 35 days to rotate in its own axis, and the equatorial region in its equator, the sun takes 25 days. So what is the reason behind it that sun takes 25 days in its equator, and it takes large number of days to cover its axis in equatorial region, polar region?
So the exact causes of this differential rotation are actually not entirely understood. Like if you are going into the details of the first decimal point of number of days, why does the sun move at exactly that rate up top and not as fast down low? But the general understanding is that because the sun is basically a hot ball of gas, right? What ends up happening is the gas can set up local convection cells, right? So, for example, when you're boiling water, and convection cells, I'll use this example of boiling water, is that if you don't do anything else, and you just put water on gas, and you have a perfect vessel which cannot exchange any energy from anywhere, what you'll see slowly is that a hot bubble will form at the bottom end where heat is being supplied into the vessel, and that bubble will slowly rise, and as it rises up, it actually gains speed, right? And so it pushes material away, and it rises up. Okay, and this is not really a bubble of air; it's a bubble of water. It's just that it's a bubble that is moving much faster than the water around it. The reason why this happens is because your pot doesn't get heated evenly everywhere. If it was heated up evenly everywhere, perfectly evenly, you would not see convection. The reason why convection happens is like a mass of water which was closer to the source of heat will rise instably and exchange this energy that it gained from near the source of the heat with the material as it moves up. Okay, something similar goes on in the sun, towards the core of the sun, and actually every layer of the sun. And that causes things to have a slightly different drag. Okay, and if you want to take a slightly even easier approach towards understanding it, is that really up top you are not only experiencing gravity, you're also experiencing the topmost layer of the sun slipping. Right? So it's rotating and slipping. And so it looks like that the topmost layers are rotating slightly slower than the bottommost layers. Also, if you think about it from just the centrifugal argument, the material that's sun is a little oblate, so the radius up to the poles is slightly lesser than the radius out to the equator. So materials, there's all these different reasons for which differential rotation is taking place, and that causes the polar regions, the cells in the polar regions to move at a slightly different rate than the cells in the equatorial region. There's also the thing that I'm brushing under the rug is magnetic fields. As I said, people don't like to invoke them unless they really, really need to. But almost always magnetic fields have something to do with anything astrophysics. And there's different magnetic braking that different layers of gas sees at different parts of the sun.
Right. So we'll take last question from Lucky Agrawal. Lucky, you can unmute yourself and ask the question.
So if we imagine a black hole in 3D, what's behind it? What's behind a black hole?
I'm not sure. What do you mean by that? Can you expand on that question?
So if we see 2D images of black hole, it shows a event horizon and a singularity. But if we imagine it in 3D, what's behind it actually?
Well, whatever space. It's there's replace the black hole with a star. It's the exact same thing because there was a star right before it turned into a black hole. Actually, the influence that the black hole has in the locality where that star was is very much limited to where you see the event horizon, and event horizons are typically always smaller than the size of the star itself. So whatever was before. I do want to see. There is another question from Tripti Dixit. Might have got left. M2-9. M2-9 is a beautiful, beautiful planetary nebula. It's the wings that you see on it are due to, however, the star that created this planetary nebula ended its life. But typically, the end results of stars' lives are explosive, regardless of what's the mass of the star. So our sun will, for example, end up forming a planetary nebula and become a white dwarf. Right? It undergoes a nova sort of thing. And these explosions, due to a variety of different factors, can be very axis symmetric, which gives rise to planetary nebulas that you see, like the Ring Nebula, for example. It's a very popular planetary nebula in, where is Aluda? Vega? M17? Does anybody know where's the Ring Nebula? I think it's close to Vega. Am I right? Am I wrong? Can anyone confirm?
Near the Lyra constellation.
Lyra, right? Yeah. So okay. M2-9 is an example of actually asymmetric planetary nebula. And so what you see is really this beautiful butterfly structure that is ionized gas that is flowing away from what would have been the star, and the bright white prick in the center is the white dwarf. There's another one about quasars are really interesting to study. They're the brightest objects, one of the oldest objects, tell us about early universe. They're really fascinating. Agree with all of the above. Quasars are, you might feel that they're really bright, but actually they're kind of dim. They're just really bright for how far away they are. So they're really the brightest objects at that time in the universe, pretty much. Quasars are also supposed to be a transitory phase. So basically, the black hole at the center of a galaxy becomes very active at some point in time, and it basically starts putting out energy as efficiently as any process can in the universe. Actually, accretion-based energy, which is what black holes do, is much more efficient than fusion, for example. So if you think fusion is the future of energy, black holes are much further ahead of you. But anyway, we can't create them in labs, so that's okay. We can't even do fusion in lab right now. Anyway, but yeah, quasars are typically understood to be a very violent phase in the evolution of galaxies, and typically they disturb the stellar populations, they disturb the gas and dust around while they are in that active phase. But they're also understood to be very self-regulatory. Like when the galaxy, for example, let's say it's forming a whole lot of stars, it's getting a whole lot of gas to do that star formation. Anything that a galaxy can do in excess can provide a sort of a feedback to it, which will kill the process that's driving the excess. So that's galaxy scale feedbacks is pretty much understood to be the next sort of step in our understanding of galaxy formation and evolution. And we really need to understand how different physical processes connect to each other to provide this feedback. And quasars are an important phase in that life cycle. Okay.
Sir, I have a question.
Okay, go for it.
Sir, the widely accepted theory is that Big Bang created universe. So, what created the Big Bang?
Well, you're basically asking a question that's kind of a. I've asked myself this question quite a few times, and more intelligent people than me have answered this in the sense of Big Bang is not an event. Big Bang is the origin of time and space. So there is the question to ask there is really we need to understand what are the mechanisms which would create, right? And typically the Big Bang is presented to as like an explosion. So you want to see some explosives put somewhere, and then they create, then they go boom, and they put out matter and light and whatnot. But Big Bang is not that. Big Bang, the unfortunate nomenclature gives it a more explosive look, but the Big Bang really is in a way how theoretical physicists would describe is a phase transition for the universe. And that's why it's a theory, because we cannot necessarily confirm what kind of phase transition it is. And so in the Big Bang tree of theories, there are hundreds and hundreds of branches. Forget about the Big Bang theory. In the inflation part of the Big Bang theory, there are hundreds and thousands of theories how inflation took place. And those theories, actually, we are getting to a point where those theories predict certain observables, which in the next 10 to 15 years, maybe 20 years, we will actually be able to measure. So we'll be able to rule out some of the theories and still we'll be able to reduce the library from which we get to choose, right? And every reduction that we make brings us closer to a better understanding of how the Big Bang happened. Right? There are lots of other theories of whether this is a cyclical thing. Is there a Big Bang happening in our universe somewhere right now, which is creating an alternate or a universe in another set of dimensions that we have access, other than the ones that we have access to? And these are all things that are very admittedly much beyond the understanding of my tiny little brain. I have tried to understand them just enough to have a conversation with you guys, probably, and maybe some of you understand these things much more than how I do, because you get to refresh this stuff, and my knowledge is basically from 4-year, 5-year-old courses that I took with some people.
Bhaiya, one last question.
I would like
Go
to
ahead.
request students to
Go on, Divyam.
yeah. But then, okay, this is the final question. Tushar, go ahead.
Very last one.
Yeah.
The planets nearer to the star or the sun that we have almost a circular orbit, while the planets far away from a star have a more eccentric orbit. Bhaiya, what could be the reason behind this?
That's not 100% correct. But the reason for what I think what you're trying to ask is the minor planets that are some of them, which orbits of which have been used to predict the presence of a planet 9, for example, that has been in the news for the last 5 years or so, 4 years, I think, at this point, is that there is a certain preferred inclination and eccentricity for orbits of bodies further out in the solar system, and that preferred inclination and eccentricity can only be explained if there is a body as massive or more massive than Uranus or Neptune, sitting much farther out from where all these other objects are. And so this thing is a actually, if you ever get to study a little bit of celestial dynamics, and I hinted to this a little bit before, as soon as you add a third body into the equations of gravity, things become chaotic. You cannot solve them exactly, right? And so what ends up happening is now you have Uranus, Neptune, Saturn, Jupiter. There are a bunch of tiny bodies that are sitting out there, right? And so these 4 interior planets, and along with the sun, they form the bulk of the mass in the solar system, right? They are trying to basically make everything perfectly nice and circular, right? Every now and then, because of the relative orbits of Jupiter, Saturn, Uranus, and Neptune, every now and then some of them line up together and they give an extra kick to the eccentricity of objects outside of where they are, and some of them actually anti-align and they give a different kind of kick to the inclination of objects. And so these kicks are what are parts of the chaos that multi-body gravitation results in, right? And whenever you're solving a gravitational system with multiple bodies, you end up with these sort of excitations, inclination excitation or eccentricity reductions, and that's what ends up giving you a preferential eccentricity and inclination. So that's most of it. The video that I sent about the evolution of the solar system will probably give you a slightly better idea about what is our current state of the art understanding of why these things are in a different orbit than most of the major planets are. All right.
Okay, it's over 1 a.m. for Amit Bhaiya.
Oh, it's not. I'm on the Pacific coast, so it's only 10:15 for me.
Oh, that's good. But still, we have taken a lot of your time. Incidentally, today, Amit Bhaiya's favorite physics teacher has his birthday. Mr. Sunil
Oh,
Pathak.
Pathak.
Yeah, he's currently serving as the vice principal of Jawaharlal Nehru School.
Kya baat hai?
Uh, do you have any closing remarks for the students of Madhya Pradesh? These students will be giving online astronomy quiz soon, a product of which is before these students. And any closing remarks, any final message before we end this?
Well, I mean, studying science in general is an exciting pursuit, regardless of whether you choose to do science as your profession or not. It is it gives you a healthy understanding of the world around you, and I personally believe that it's always better to ask questions than to take things at face value, right? So sometimes our elders not necessarily respond to it well, and I understand that skepticism, right? Like I still get scoldings from my parents about you don't understand this, right? And I understand that experience probably is a very important factor in the growth of a person, but science will almost always equip you to not only understand the things that you're studying, but also, as long as it's a healthy amount of skepticism, right? It gives you a healthy dose of skepticism to question the status quo, to further the understanding of, okay, what I understand today is probably what everyone before me came and gave me this knowledge about, but how can I make things slightly better? How can I change? Or what kind of observations do I need to do? What kind of instruments do I need to build? And these are things that can be applied to any field of in existence. If you were to become whatever kind of engineer tomorrow, right? Or if you were to become a doctor tomorrow, you would always have to make decisions which more often than not will be evidence-based, right? You will not have a textbook in your hand always to guide you exactly what to do in a given situation, right? And I've been lucky enough to have a lot of teachers who always encouraged me to ask questions. And, more than that, asking questions, they were always very receptive of me asking those questions. I was probably never put down by any of my teachers to say, why did you come to me with this question? This is not in your book. Don't bother me anymore. And I remember one of my first interactions with Pathak sir was, I just took a 9th class physics book to him, said that I'm trying to understand how gravity works when I was an 8th class student. And he was like, Tum ye kyo pad rahe ho? But he never told me that I will not explain this to you. He was like, his next thing was, okay, show me what problem you're trying to solve. Right? And that kind of healthy encouragement, I think, is a very basis of how the future leaders in any field probably need to think. And that's, I guess, that would be my words of wisdom, if I may, I guess, grant to you is, have a healthy skepticism of everything that you encounter in your life. Ask questions. If you cannot ask to others, ask to yourself. There might be moments in time where you will not be in a position to necessarily change the answers or even receive an answer. But the fact that you asked that question will eventually always give you a much higher confidence in whatever the answer that you found. But if you accept an answer without questioning how you got to that answer, probably kills the joy of learning. And that's the most important thing. You should be able to enjoy how you reach to a conclusion, how you reach to an answer. And that's most of the fun. Once you get the answer, actually, it's more tedious. I love doing observations. I love building instruments, but publishing them is a different thing. You have to argue yourself over and over again and make sure that every sentence that you write in a paper is vetted exactly. Okay? And that's where I said the healthy amount of skepticism is important, because sometimes you can have an unhealthy amount of skepticism and you self-sabotage yourself. Don't do that.
Okay, I would now request Sri Alok Mandavgane, who is the Joint Secretary of Aryabhat Foundation, or also known as Aluda, to give a proper vote of thanks to this session.
You're muted. Boom.
Yeah. So thank you, Amit, for this wonderful talk. So I think some of you might know, Amit and I went to Nainital together. So I only have had opportunity of one trip with Aryabhat as a student, and that was to Nainital. And so I've had great memories too. Visit Nehru Planetarium, Delhi, and Nainital Observatory. So we had fun there. So
And we gave
thank
a
you, Amit.
presentation on giants of the solar system.
Yeah, I still remember we gave the presentation to Professor Ram Sagar, and he was the head of ISRO at that time. So
Head of Aries.
Aries, yeah. No, he was with ISRO also, I think.
He was, but he was the head of Aries.
Yeah.
And I think then he went on deputation to IIA, and I think afterwards he retired.
Yeah. So he's still active. I got in touch with him recently.
Yeah.
So yeah, good memories with Amit. So thank him to encourage our students, and I thank the students to have such an interactive participation. I would encourage them to ask even more questions. So initially, I think they were a bit hesitant. We would like them to take the opportunity and ask more questions next time. And I would like to thank Divyam here for coordinating and organizing such a taking such a nice initiative, and also like to thank Shreyas Papat. So his face you would not have been able to see right now. He's working hard to make the live stream possible. So this video right now will be accessible for future as well for everyone to see. And so thank you everyone for coming to this session.
All the mistakes are mine. Don't kill me in the comments.
So thank you everyone.
Okay, guys, before you exit,